Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to today's webinar, Modular Block Retaining Wall Design and Build. My name is Amanda and I'll be your host for today. Firstly, in keeping with our custom, Engineers Australia acknowledges the traditional custodians of the country throughout Australia and recognises their continuing connection to land, waters and community. We pay our respects to them, their cultures, and to elders past and present. Before we get started, I'd like to acknowledge that today's webinar is being hosted with Engineers Australia's long-standing industry partner, Geofabrics. Geofabrics has been in the business of geosynthetic engineering and infrastructure development across Australasia for over 40 years. With expertise in roads, rail, coastal, mining, waste and defence, they help clients deliver and maintain infrastructure by minimising risk and increasing value through the use of geosynthetic product solutions. Geofabrics has supported significant projects such as the Victorian level crossing removal and the Christchurch gondola in New Zealand. On these projects and every project they undertake, they have a singular focus to protect, contain and secure the physical environment for future generations. Today, we will hear from two speakers, followed by a live audience Q&A, and I encourage you to send questions through to our speakers via the chat box. I'd now like to welcome our first speaker, Liam Donohoe. Liam is a civil engineering manager at Veri-Block with over 15 years experience in the construction industry and retaining wall systems. For the past 9 years, he has focused on supporting projects across the European, Middle East and Africa and Latin American regions, delivering innovative and cost-effective earth retention solutions. Liam works closely with producers, contractors and designers to adapt precast concrete systems to local markets. Passionate about engineering excellence and sustainable design, he combines technical rigour with practical, field-based insights to drive high-quality outcomes. Please welcome Liam Donohoe.
Thank you very much for that introduction, and welcome to today's presentation on Veri-Block Precast Modular Block Retaining Wall Systems in association with Engineers Australia and Geofabrics. Today we're going to have a quick overview of the evolution of retaining wall systems. We'll then look at what precast modular blocks are and where they came from, a product overview of Veri-Block, and then a review of our technical resources available and some of our software partners for design and analysis. Retaining walls have existed for thousands of years. Ever since the human race became an agrarian society, they were needed to cultivate land and herd livestock. Essentially, the first retaining walls were masses of boulders, debris, rubble, held together with different types of mortar and to create a heavier mass than the soil body that they wanted to retain. That method or approach remained vastly unchanged for thousands of years, until around the late 1800s. One notable evolution was in Bologna in 1979 when a company called McAfee standardized the concept of filling woven baskets with a mass of rocks or debris. The idea or concept was to create a uniform dimension and known weight so that the mass of the structure could be calculated to determine how much was needed to retain the earth. The word gabion actually comes from the Italian word gabione, meaning very large basket. The next notable stage in our evolution of retaining walls was in the early 1900s. As reinforced concrete became widely used in construction and more understood, people started using reinforced concrete in retaining wall applications, in particular cantilever walls. The idea with a cantilever wall is to create a structure with a heel at the back at which the soil is placed on top of, and the soil mass creates generates the weight to resist sliding and overturning. In the 1970s, thanks to the efforts of Terzaghi, we began to broadly classify retaining wall systems. The more common ones were the gravity wall and cantilever wall. Our gabion baskets today wall classification, whereas cantilevers would obviously fall under our cantilever. So people ask, what is a precast modular block? Well, in the late 1990s, people began pouring concrete into large cubes and creating different forms to experiment with. Some of them, the first ones in Europe were the Benton block or Kelly block, Lego block. And then in the early 2000s, people began to standardize them to try and generate retaining walls. We've come up with a very technical diagram to explain how these retaining wall concepts work with precast modular blocks. They're essentially Lego. They stack together exact same way. No mortar, no bond, no mechanical connection. It makes it nice and easy. The benefit of modular block systems is we use all the same benefits as reinforced concrete, but in a factory controlled condition and without needing to excavate to install the heel. Because the blocks stack together, we can install them far quicker and with less excavation. The term prefabricated modular block comes from the modular nature of the system, with standardized face dimensions and extendable depth to achieve taller gravity walls. For example, our standard block is 914 millimeters deep. However, that can be extended to 2.1 meters to create a heavier mass and moment for resisting the lateral earth pressure. Some of the main features of the Veri-Block units or system is the hollow dry stack interlocking nature. We keep a void through each of our blocks to allow for installation of drainage components at the bottom of the wall, reduced freight weight by reducing the concrete in the units, and by creating a large shear lug, we generate a significant interlocking shear connection, resisting the lateral earth pressure. The units are sized for civil and residential use and are produced with wet cast concrete. Due to the large face of the blocks and reduced weight because of the void, we can achieve 25 square meters on average per truck. If we look at the face dimension of a Veri-Block unit, it's 0.74 square meters, meaning we're on average 40% larger than other PMBs on the market. However, we still use 40% less concrete per square meter. Due to the increased size, we can save on average 25% during the installation time. The void, as I mentioned, is used for installing the drainage composite at the bottom of the wall. We backfill this with free drain and aggregate, as you can see here. The motive for this came from the developers of the Veri-Block unit, who were contractors in Utah. One of the main criteria that they wanted in their system was to be able to install drainage without it being crushed or deformed during the backfill stage and compaction. Generally, the drainage column is installed to the rear of the retaining structure, and as you backfill and compact, the perforated drain pipes kept getting crushed, and this became an issue for a lot of the projects, as 90% of retaining walls would fail due to water. So we wanted to ensure that the drainage could be easily installed, viewed, and protected. We increased the mass, as I mentioned, but we also try to maintain the concept of a hollow core unit. You can see here that we have a 2.2 meter deep block. It weighs 1,600 kilos, and we can achieve retaining walls with mass gravity up to 6.8 meters. We have a height guide showing standardized heights that are achievable based on various soil conditions and loading conditions, such as a surcharge of 12 kPa or a 2-in-1 crest slope on the top of your wall. These are guidelines provided to allow engineers to get an approximate estimate of where they will start with their retaining wall project using Veri-Block. If required, We can modify the shear load configuration of the units and increase the setback to 300 millimeters, 12 inches. This in turn creates a reinforced slope as it's 26 degrees rather than a retaining wall. We also have the preliminary height guide available to give an approximate configuration for your wall or project. One of the largest evolution points in retaining walls was the introduction of mechanically stabilized earth. It was a concept that existed in Egypt thousands of years ago. There's evidence that the Egyptians would use woven fabrics or reeds to tie between sand layers and reinforce it for slopes or install stone structures on top. In 1963, a French engineer formalized the mechanically stabilized earth system and called it terre armée, or reinforced earth. These have become some of the most popular retaining wall systems in the world. And the concept was using mechanical strips connected to the face to stabilize the earth itself and use that as the mass retaining the earth at the rear of the structure. Although they're very common, they're not without their issues. Notably, some of the main issues is the serviceability of the systems. Due to the vertical face, installation is slow, on average by 35 square meters per day with a standard crew. However, these can go out of plumb and need to be dismantled and reinstalled. Other notable limitations introduced recently are the limitation on railway applications. Due to the non-extensible steel straps at the back of the units, they are a high risk for electricity. They also corrode quite quickly in corrosive soils, meaning that your retaining wall structure might have a reduced service life from 60 to 35 years in extreme conditions. With the need to go taller in certain applications, Veri-Block can be used as an MSE system. We typically recommend a geosynthetical reinforcing net. These are placed between the units to generate a friction connection. Between each unit, we have 1 square meter of contact area. And again, because of the hollow nature of the blocks, the geogrid reinforcement is not generating friction between concrete on concrete, but also crushed stone between crushed stone, meaning we get a very strong pull-out resistance for those friction connections. If required, we can also modify the geogrid to a 500 mil wide strap and place it through the void in the block and create a positive connection system. These are more applicable in the areas of high seismicity or high surcharges, where the connection is the governing failure mode of the retaining wall. As Veri-Block is produced with wet cast concrete, one of the main benefits is the viscosity of wet cast concrete, meaning it can take the form of many shapes. To leverage that to our advantage, we create polyurethane liners at the bottom of our forms that create natural looking rock textures. But these are interchangeable, meaning we can create different textures using one form. For example, our most common texture is a canyon ledge. That's 14 variants to make a more natural, non-repetitive texture on your retaining wall solution. More recently, we've seen an increase in demand for the cut sandstone, particularly in Europe, where people want the retaining walls to resemble the more natural cobble walls that farmers would have built over the past few hundred years. However, in certain projects, there's a need for custom textures. Recently, we had a project in Hawaii where the local municipality required the project to look and fit into the current aesthetics, meaning we had to create a custom lava texture. Although it's quite cool, it hasn't taken off outside of Hawaii, although I am quite a fan. Another bespoke solution we've come up with this year was the rail sleeper texture. The need for this came about from the UK, where people are used to seeing retaining walls built with recycled rail sleepers. However, as these sleepers corrode and rot over 20-35 years, local municipalities want a more long and enduring retaining wall structure. That's where wet cast concrete comes into it. Increased longevity and the certification for 120-year design life. However, to avoid annoying residents in local areas, the request is that we provide this custom wood texture. So it would look like what they were used to, but last longer, increasing asset management and longevity, and also being more sustainable. As opposed to installing a new retaining wall every 30 to 40 years, you install one that lasts 120. Where are most Veri-Block walls used? Initially, Veri-Block was developed for landscaping, housing, and aesthetic purposes. However, due to the increased size but reduced volume of concrete, it became more cost competitive, and we've seen an increase in infrastructure projects due to the cost savings. Throughout the world, in our network of producers, we see various applications in highways, particularly due to the quick installation, but also reduced footprint, meaning that we can reduce the excavation against site boundaries, reducing the requirement to purchase land or compensate owners for intruding on their property. We've also seen an increased use in water applications due to the fact that these blocks are not reinforced. In water, there is no risk of corrosion. Large logistics centers as well are using modular systems to generate more usable space for trucking and freight to optimize and increase logistics and their supply chains. You can see here another example of water applications. This one in particular is in North Carolina. It was required by the local environmental agency to accommodate the spawning of different marine life along the wall, which is why we have the riprap there as well to create nesting areas, but also the longevity of the wall. Not having that reinforcement means that the blocks won't corrode and rust over the next 40 years. The installation, as I said earlier, is like playing with Lego. They stack together, there's no wet concrete or mortar on site. You backfill your drainage material in the void, place the next block on top, and repeat. The main criteria to get right during your installation is your base course. If your base course is not level, it can cause the blocks to sit or tilt on top of each other. This issue can be exacerbated and exaggerated as the courses go up and can create an eccentric load on the center of the bottom blocks and could cause them to crack. That's not an issue isolated to Veri-Block, but all large block solutions. So whether it's Veri-Block or other systems, I would encourage you to make sure that the base course is installed correctly. Once that's done, you just have to go and place the next ones on top. We have a short video here showing how easy it is to install one of these units with 2 men and a 13-ton excavator. You can see that he cleans underneath the block as it's suspended to ensure that there's no debris stuck there that might cause the block to rock. Once the blocks are lined up, the operator on top can look through the void and ensure that the block engages with the shear lugs of the blocks below it. Unhook the excavator, and he's ready to go. In certain markets, however, particularly ones where labour is becoming more expensive or harder to obtain, we've seen operators and contractors become very creative. For example, in this project in Tennessee, the contractor used a hydraulic grab on top of his excavator to install the blocks without being required to hitch or unhitch the blocks. One operator followed to ensure that the excavator did not track over the geogrid rolls at the back and ensure that the blocks were fully engaged. There were 2 more operators who followed and extended the geogrid and then backfilled with a bobcat and compacted. The 4-man crew were able to install 51 square meters of retaining wall in 30 minutes. You see how quick this is. This particular project was achieved, or this installation rate was achieved because they were able to stage the blocks close to the wall and on a straight run. However, it's still achievable on larger projects as well. Due to the seismicity of the area and the height of this wall, it was decided by the local engineers to design it as a tiered wall to reduce the pressure on the bottom courses in the event of an earthquake. Collectively, the combined structure was over 20 meters in retained height. One of our main components for any retaining wall that is your drainage composite at the back. 90% of retaining wall is due to hydrostatic pressure, so we want to ensure that we have good active drainage. In this scenario, the contractor is backfilling with a finer sand material. What we don't want to happen is that that finer material migrates into our drainage column in the blocks. We put a non-woven fabric along the back of the units. This is quick and easy to do, and you can see that it's as simple as holding it down with rocks on top during the backfill process. Compaction is important too. Each country or state will have their own recommendation and guidelines for compaction. In general, we recommend compacting to 92 to 98% proctor to ensure a reduction in displacement of the wall over the settlement course of the first 6 months is typically when your active earth condition is engaged. Each retaining wall will move slightly, it has to, if it's a yielding structure. But we want to ensure that the compaction is achieved to an adequate level to minimize that lateral displacement. Here we can see an isometric view of a standard Veri-Block retaining wall section. We see that the backfill material was installed at an angle, which is determined by your geotechnical engineer. Typically, we align that with the natural angle of repose of the retained soil. And the backfill material used is normally better than the retained material to optimize your wall cross section. As our blocks are tapered, we can achieve concave and convex curves. This provides more aesthetic appeal, but also mitigates the need to install cumbersome corners, which can be complicated on site for contractors. Some of the resources we have available are the following. We have a library of blocks and units. We also have all these units available in DWG format or AutoCAD. If you'd like, we can share this. The idea here is that you can draft or draw your own wall, but each block on AutoCAD is combined and has the attributes of the wall, of the block mass, weight, and area, meaning you can pull your volume or concrete volumes very quickly using the data extraction tool in AutoCAD. We also work on a library of standard details. So as we engage with contractors and installers, we typically find that they'll ask us to come up with a bespoke solution for a project. Each time we do, we ask ourselves, is another contractor going to face this issue? And if we think the answer is yes, we put together a standard detail and publish it on our website. The idea here is that for contractors and engineers to lean on us to solve their solutions to increase the efficiency or reduce the time needed to work on your own project or install your wall. Some of the more common details including our drainage through the bottom of the block. But one thing we wanted to highlight was our 45-degree corner block. We are the first and only large block solution with a dedicated block for 45. This came about due to the request from several contractors who had to install 45-degree corners on property lines. The issue was the requirement or need to cut blocks on site to achieve that angle, as most modular systems work in a 90-degree angle or a curve. We're quite happy with the results, and the contractors are very, very pleased, as well as the homeowners. We also have a library of standard data. A lot of engineers like to put together their own internal spreadsheets for calculations, or, and rightly so, they like to doubt software. They like to verify the data and make sure that the software is providing an accurate and realistic answer. To facilitate this, we provide a library with our infill calculations, showing the center of gravity, the mass, the infill unit weight of the blocks, and the combined unit weight used in the calculations. These are available for all units. In addition to this, we also provide laboratory test results. In order to accurately and confidently design retaining walls, we like to verify that data is factual and not theoretical. To achieve this, we partnered with TRI laboratories in Texas, and we've carried out a series of tests, including interface shear tests, as you can see in the image on the top, where we place blocks on top of each other, fill them with aggregate, and then applied a load cell at the back and a hydraulic press and forced the blocks to displace laterally and see which was our main failure mode. This data is correlated and used for input into design and analysis software. We've done the same for the friction connection test with GeoGrid, as well as our positive connection, as you can see at the bottom. We ran the grid through there and applied the hydraulic press and forced the block to displace laterally and determine which would fail first, the GeoGrid or the block. A lot of architects and landscapers like to design their gardens or solutions in SketchUp. For that reason, we've actually provided our full library in the SketchUp 3D warehouse, which is available, and it comes with the textures. On our website, you can download the PDF of our design manual, which has our standard construction details in it, as well as installation guidelines and recommendations for best practices. We also include specifications for minimum product strength, such as the compressor strength of the concrete needed to align with the test data obtained. Lots of people do ask, okay, this is cool, how do I design it if I don't want to put together in my own spreadsheet? We have a software which you can download from our website via the Toolboxes tab. Alternatively, for the Australian market, you can contact myself or Eric Yoda directly, and we'll send a modified version with the GeoGrid supplies that are available in the Australian market. Next, I'm going to redo that one because it froze. I'm just going to wait here for 2 seconds. The main criteria that the software will assess is internal and external sliding failure. That is determined if the wall is going to displace due to the lateral pressure from the earth at the rear of the structure. It'll also determine the overturning. It'll make sure that the width of your wall is broad enough to provide enough resisting moment compared to that of the lateral earth pressure. It'll assess the burn failure to make sure our wall doesn't fail through that mode, as well as a simplified global stability analysis. The info we require to run a section on this software is primarily our bottom of wall level and our top of wall level. Once we have that, we can determine our exposed height, block height, and the wall height. The exposed height is your wall height minus your embedment. We then have to input if we data on a slope or angle, if we have that at the back of our structure, if it's not a level crest. And we can offset that as well. So the further back we put a slope, the less pressure it will impose on the retaining wall structure itself. We then need to input our backfill material and foundation soils. We have 2 soil bodies. The data required will be your unit weight, cohesion if applicable, and internal angular friction. And we have an option for select backfill. If we want to mitigate poor soil conditions, we can allow for a granular soil wedge to retain the natural material. And this is a good way for increasing the efficiency of a retaining wall section by reducing the mass needed in the blocks by using better material over the native retained material. Within the software, we have the option to import a PDF. When we import the PDF, we can trace the line of our wall, as you can see here outlined in red. We can then input our top of wall levels and bottom of wall levels, and then based on the critical cross section that we've analyzed, the software will automatically generate a wall elevation. This is a great tool for quick estimating if you're pricing a project, but also for the formal design, as you can export this to a format that can be imported into AutoCAD, and it reduces your drafting time as well. It's typical output or checks for the software. As you can see here, this is checked in accordance with the NCMA standards. But we're aware that not everybody works with proprietary software. A lot of engineering firms will have in-house software or work with external partners, which is why we've been working over the past 2 years with several partners such as Fine, Rock Science, and CTI Software. All the softwares mentioned are currently working on or already have imported our library of units, which means you can access them directly from the software instead of having to input the data manually. If you have any questions or would like any support on a project or prelim, you can contact myself or Eric at any time. We're always happy to help. And we want to make sure that you can find a solution easily for your projects. Thank you very much for your attention.
Thank you, Liam, for a great presentation. I'd now like to welcome our second and final speaker, Eric Yu. Eric is a highly experienced specialist engineer with over 27 years in the field. He brings a wealth of technical expertise in designing reinforced soil slopes and walls, slope reinstatement works, slope stability analysis, embankments over soft ground, pavement stabilisation, and rockfall protection structures. Throughout his career, Eric has accumulated diverse international experience across Malaysia, New Zealand, and Australia. Notably, in New Zealand, he contributed as a member of the panel for the development of the MBIE Rockfall Protection Structures Design Considerations Guideline. Please welcome Eric Yu.
Yeah, thanks for the introduction. My name is Eric. I'm the technical BDM for Slopes and Wall for Geofabrics. So the second part of the presentation today on the large-scale precast modular block retaining wall system, Veri-Block. This is the agenda that for my part of the presentation, which I'm going to cover the most commonly used Veri-Block types of blocks. And then as Veri-Block can be used with a mass gravity retaining wall systems or geogrid reinforced soil system, this is one of the frequently asked questions on when do you use them. And I'll show that in my later slides. And then this presentation is going to end or finish with some case studies or in Australia mainly, and we'll complete the presentation on that front. So the most common Veri-Block blocks, which we call standard blocks, are 1.22 meter wide by 0.6 meter high and 0.9 meter into the soil. You have seen earlier on, Liam presented on the Veri-Blocks. This is just a bit of a recap. So just bear in mind that these Veri-Block systems are wet cast, so 40 MPa concrete compressive strength. They are now ASTM standard C1776 and 1776M specification only on this type of wet cast concrete retaining wall systems that you can download or free to get a copy from us. One of the important features for the Veri-Block systems are the shear lugs. This is one important feature that provide very high shear resistance between interblocks, top and bottom of blocks, and have a very high shearing capacity to prevent sliding. The blocks are also hollow core to be filled with drainage aggregates. With that, the entire systems are free of pore water pressures. They weigh around 800 kgs each for these particular standard blocks, and that covers the front face area covers approximately 0.7 meters square per block face, front face, or approximately 1.34 blocks per square meters of face area of the retaining wall. The other common types of Veri-Blocks are top blocks, the one that are on the top left corner. They are normally used at the top and upper portion of the retaining structures. You can see the back of the blocks are a little bit lower than the front. That portion of about and around 200 millimeter thick are for allocations of either you put some topsoil for vegetation, lawn, or it can be simply cast with concrete or barks or the type of things that you're going to put on top. So these are top blocks. Then, of course, there are half-step blocks to somewhere in between the transition between the walls surface area, and half-width blocks, and also corner blocks, and mass extended block, particularly when a mass gravity structures of certain height exceeding certain height is required. These 5 types of blocks plus the standard block earlier shown, 6 types of blocks, will probably cater for most of the wall block types for most retaining structures 95% of the time. There will be some odd cases of different types of blocks, but if you are familiar with these 5 types of blocks, you probably catered for most situations already anyway. Now, whether or not, as mentioned earlier on, due to the self-weight of the block and by means of using in certain situations mass extended blocks of either 1.2, 1.5 is up to 1.8 meters, you may construct mass gravity structures without the need of additional geogrid reinforcement. There are situations where geogrid reinforcement is required with the use of only standard blocks without the need of max extender for certain situations. When we mention geogrid reinforced, the one on the right, it basically means that with inclusion of geogrid and sandwich in between the blocks, the vertical blocks as a facings, the entire mass, soil mass behind the blocks becomes a composite reinforced soil mass that are self-stable to resist against lateral earth pressure at the back of the geogrid. And geogrid becomes a part of the internal stability design, which is going to cover a little bit after later on in the presentations. So when do we use a mass gravity and when do we use a reinforced soil wall? Very much of that comes down to how high is the retaining wall. This is by far the most important factors deciding the types of system between mass gravity and reinforced soil. Obviously, there will be some overlapping in certain situations. It cannot be a simple cut in terms of height only, but those overlapping would depend on and is a function of designs in most cases, foundation soil and retained soil strength. Is the retaining wall designed for a cut of field conditions and the type of material that you're cutting? Or if the retaining wall is supporting on an existing downslope, or whether there will be a slope that is going to be proposed on top of the proposed retaining wall, the types of surcharge loading that you are designing, and if there is any earthquake loadings, and what are the types of peak ground acceleration that you're designing for the retaining walls, and the type of hydraulic conditions. These 6 points, what I call are the design conditions, dictates whether or not a more suitable type of wall system, either the mass gravity or reinforced soil systems are required. And obviously, all these conditions are the design factors to meet the stability of the wall from the various failure modes the retaining wall needs to design for. So when we talk about failure modes, there are external and internal stability reasons or factors for the design of the retaining walls. The external stability comes down to if the wall is able to resist the lateral earth pressure from a base sliding point of view, or the wall is bulk enough or heavy enough to resist an overturning type of scenario, assuming the entire wall as a single unit of wall structures. And when the wall is constructed on an existing ground condition, whether that foundation ground is good enough, competent enough to support the wall from a failure condition into the ground condition, into the ground that you are placing the wall, and which we are referring to as bearing capacity. That's external stability. When it comes to internal stability of a modular block wall, we're talking the internal unit-to-unit shear, whether they are capable of resisting the lateral earth pressure, not just on the base of the wall, but in every single layer of the units. And then obviously, every single layer needs to be checked whether they can resist the overturning type of a failure mechanism resisting the lateral earth pressure. The last type of mode that usually a retaining wall designer should and would check is that whether a slip circles, or we call it slope stability type of failure modes, is a critical mechanism for the retaining wall, particularly when you have, say, a concern on the softer foundation ground. This is the type of mode of failure that a designer should be aware of and should check typically. And the check can also be extended to slip circles. Stability check can be extended also to every single particular layers of the internal shear unit of the modular block wall. Now, when it comes to reinforced soil structures, particularly whereby the geogrid reinforcement plays the important role of reinforcing the mass of soil behind the facing blocks, we are checking to ensure that, number one, the connection strength between the geogrid and the facing is good enough, that they do not get a pull out from the facings. Number two, the geogrid layers that you lay are strong enough to mitigate the shear planes of the soil. And number three, they are long enough to prevent the pull out from the soil. These are the three main checks when it comes to internal stability checks of a reinforced soil structures. When it comes to reinforced soil structures, external stability, i.e. the sliding, the bearing capacity, and the overturning are not too much difference to the standard conventional retaining wall checks mentioned earlier on. So one thing to note before we move on to show you the difference between the particular height that we're going to compare whether a mass gravity or reinforced soil is important. Just one slide to touch on the importance of the use of the soil parameters in the design model. And this is because soil makes up of the areas around a retaining wall, surrounding the retained material behind, structural field, foundations. So this is the single most important factors that impacts the wall design and obviously constructions and performance. From a design perspective, the real art and science of a retaining wall design strictly comes down to how these soil parameters are used when running the calculations. It is much more important and accurate soil parameters is used more so than how accurate a calculation is performed. Soil parameters controls lateral earth pressure coefficient K, and therefore from a long-term design perspective, a long-term effective stress soil parameters, the C dash and the phi dash should be used. And this means trying to limit the cohesion value even with clay soil. One exception of using cohesion, particularly for the foundation, is when a seismic load case is used, whereby a short-term undrained shear strength type of parameters for clay may be adopted for foundation for seismic load design, simply because seismic design is a short-term design where the motion of shakes and movements only occurs in a few seconds. So there is a particular case when the short-term undrained shear strength can be used for the foundation soil. Now, whether or not a mass gravity or geogrid reinforced soil is used, we shall look at one consistent height, and we will compare the scenarios. So this one particular height is around 2.74 meter high, not overly tall and not overly low either. And usually is a cutoff, is a overlapping scenarios. It can sometimes be mass gravity, sometimes be geogrid reinforced, sometimes require mass gravity and sometimes not. So you will see these two particular cases here where we have a cut conditions with existing ground with a fairly competent soil parameters of C dash of 5 kPa and friction angle of 38, similar to the competent foundation soil condition, whereby up to this height, the standard unit can be used without needing the mass extender unit at the base. Whereas the case on the right, we have a field condition with weak to moderate type of a field soil with friction angle of 28 degree and C dash of 0. Similarly, a weak to moderate foundation whereby a 1.5 mass extender is required even with the same height. The next scenario comes down to when you have an existing downslope and you are constructing a retaining structures of 2.7 meter high, similar height, on top of a slope whereby the slope global stabilities plays an important critical mode of failures where you are wanting to improve the slope stability factor of safety to say safety factor of more than 1.5. And in this particular case, you need to include in geogrid to intercept with the potential slip plane to bring the factor of safety up to 1.5 with the type of moderate soil parameters that I've indicated there, C dash of 2 and phi of 30. I hope that shows you the difference between gravity and reinforced soil. And the sample or the example on the right is simply a wall of similar height, but this time with rather high dead load close to the face of the wall, something behind the wall, and you will see the need of a reinforcement close to the dead load location and slightly longer than and beyond the dead load, simply because that's the intensity of where the load is, and the two difference in terms of a geogrid length requirement, because the one with the dead load is not founding on existing slope. These particular examples here shows a seismic loading of around 0.4 of a G, quite a fairly high seismic loading, but obviously because of the moderate height 2.74, the significance of the demand on the geogrid length, you can't see it that much. Otherwise, usually with higher seismic loading, the geogrid length usually becomes longer. We talk about the L/H ratio, so the length of the reinforcement versus the height of the wall. Usually the L/H ratio for the seismic loading are longer than the static load case. The last example on reinforced soil structures comes down to, say for example, you have a rapid drawdown condition. This wall is constructed in a narrow channel, and there is a chance that during a flood situation, there is a rapid drawdown situation. You have an imbalance in terms of water pressure internally inside the wall and externally, and you see some, again, minor effects on the demand on the geogrid length in this type of situation. Obviously, the 2.74 is just for comparison reasons. There is no limit in terms of the height of you can build. The example shown there is up to about 3.96 meter high with mass extender block of 1.52 at the base, followed by 1.2 and the standard block of 0.9 with a moderate type of existing cut slope and a moderate foundation material. And this particular high tall structures of 9.1 meter with a top slope on the top and sitting and founding on downslope, you see the demand on the geogrid at the bottom zones or layers with long geogrid reinforcement, followed by shorter geogrid at the top, simply because we do not need that longer geogrid at the top for internal stability, but for global stability, slip circle stability reasons, we need the reinforcement to be longer for the slope stability reasons. We're now covering the case studies part. So this one particular case here in New South Wales called Red Bank South Heights, approximately 125 meters long, up to around 7.5 meter high maximum height. And it is constructed and requires because of the road upgrading and widening for the projects over there. So you can see here, this is a drone shot of the overall view of the retaining wall. This in 2 tiers. So the diagram on the right is just a snapshot from the stability analysis showing the multiple wages of base sliding for sliding stability check among the many other different checks, internal stability, bearing capacity, and global stability checks that we have performed for this particular project. We're still on the same project case studies. These are just some snapshots of different detailing on site showing how the subsoil drainage pipes is laid in within the 2 legs of the base block prior to filling in the drainage aggregates with geotextile at the back of the block, preventing the structural field from migrating into the drainage field. Yeah, geotextile laid in the middle photos. You see the geogrids are laid, sandwiched in between the blocks, ready to be fold back prior to backfilling of the structural field for compaction. So some drone shots almost up to the completion level of the retaining structures. You can see from here. And side view when the wall was completed about 1.5 years ago. Some upper infrastructure is a detailing type of furnitures on top, like a handrails on the top that you can cast onto the top of the blocks. Another view from the sides showing the completion of the 7 meter high wall founding on existing slope. Case number 2 is a slip reinstatement works in Victoria called Acheron Slip. It was originally designed as a 750 millimeter diameter board piles, but it was later on found out that the design becomes impractical due to accessibility issue, very narrow width of the existing roads, availability of the machineries, and practical installation issues basically. So fairly quickly, the engineer has contacted a quick way of constructing and retaining the slips while maintaining the accessibility of the road during constructions, and Veri-Block straight away becomes the obvious choice due to the very quick installation rate of between 60 to 80 meters square a day, with the use of what they call excavator at the top. So the total height was up to 3 meters, founding on the foundation competent layer, followed by some counterweight measures filled in front of the wall with rocks material in front of the toe of the wall. Another example showing, I think if not mistaken, this wall was about around 6 meters high in Somersby in New South Wales, supporting an industrial lot. You see some casting of the traffic barriers type of system on top of the wall. Something that can be constructed and done in the type of Veri-Block retaining wall details. This example shows the multiple lot dividing type of low height retaining walls. Some of them just 2 blocks high, so 1.2 meter high. Some of them simply 1 block height, and has been used throughout the entire development of subdivisional lots in Port Arlington, Victoria. Another examples of road dividing projects up to 4 meter high in this particular case in Eastern View Estate, New South Wales, supporting a new road constructions. Again, some road furnitures that you can see the difference between the flexible barrier constructed some distance away from the face of the wall, and then the handrail type of furniture constructed on top immediately not too far away from front face of the wall. This is a retirement village constructions in ACT, Canberra, supporting multiple different lots of retirement villages using Veri-Block. Last project is Oran Park, New South Wales. Stage 1 is has just been completed, and the contractor is about to start stage 2. This features wall height from 0.6 meter to around about 4 meters high, using only mass gravity. Okay, no geogrid, and construction for a new showroom basically for this particular project. And obviously, there are assorted type of landscape applications for residential housing with plants. You can see the buds placing on top of the top blocks, and and this particular beach access in New South Wales as well on the right hand side of the photo. I showed earlier on different type of fences and pedestrian fence, lamp posts that can be constructed on top of the retaining wall, to the details of the engineer. Due to the shape of the wall, they can be constructed either convex or concave curves. And in this particular case, Veri-Block has a 4.9 meter type of a minimum radius suitable for constructing the wall in curves rather than corners or straight bend. Obviously, when you require bend or corners, there are different types of blocks I mentioned earlier on in the second slide that they can be used. And you will see in these particular examples here how the top blocks, half step top blocks, top corner blocks, and center blocks are used in this one particular example of photos. And second to last slides, but more to do with these are the literatures or documents available from us. There are retaining wall design manual, block library in terms of the different types and fill volume for the aggregates, density, center of gravity of the blocks, weight of the blocks. You can find here. And there are also the different type of multiple typical details drawings that is available free of charge in both DWG file and PDF from us. Lastly, this particular retaining wall system is not complete without the free suites of software from the manufacturers. So this particular software can be used for either the mass gravity wall design, okay, or geogrid reinforced soil for simple geometry and ground model. And this is something that we are more than happy to share with you. And also feel free to get in touch for a demo through online, something that I'm more than happy to do. Lastly, as a summary, the Veri-Block precast modular block wall are factory manufactured. Because of that, their quality of a 40 MPa is ensured. They are ready to be used once delivered to site. So once your site is ready, prepared in terms of the foundation preparation works, and the blocks are there, you can just use a machine without much manual handling. We think that they are aesthetically pleasing and they are suitable to be used as both landscape or a very tall engineered type of retaining wall system. With this, I end my presentations and thank you very much for your attention.
Hi, it's now your turn to get involved. Please ask our speakers questions via the chat box and who your question is directed to. Thank you for everyone who submitted questions whilst registering. And we might start with a pretty big question, Liam, that's come through from Curry, who is watching in Victoria. Good afternoon to you. Asking you, Liam, what's the biggest mistake engineers make when designing modular block retaining walls? Thank you. Thanks, Liam. Okay, we'll just let Liam sort out a couple of technical issues and Eric will bring you into the conversation, go back to Liam. We've had a question from Mohammed, again, watching from Victoria, it's raining here, asking what are the main design considerations?
Yeah, thank you very much for the questions. Design considerations, as mentioned in the presentations, mainly comes down to the adoptions of the accurate soil parameters. As mentioned, these are the most important factors affecting the performance and also economical of the designs. The other considerations are whether or not the retaining wall needs to be designed for higher than normal transient loading, for example, a dead loading, and groundwater conditions fluctuations over the design life of the retaining walls. I think these are, in my experience, few most important design considerations.
Thank you for that, Eric. And just staying with you for now, we've had a question came in from Yegane, who is watching in New South Wales, asking you, Eric, how deep will you go into the retaining wall concept?
Right. I think how deep, probably how far we as a company, GeoFabrics, would go in terms of the support to engineers or our clients in terms of the design concept. Okay, if that's the questions, then it depends on, because due to the variability of our clients, sometimes our clients can be residential homeowners, sometimes the clients can be a developer of a project, or sometimes it can be the civil or the structural engineers itself. Okay, so each situation will dictate how we support the types of clients that we do. But in general, when we are faced or being provided with an opportunity, we will normally take down in terms of how high the wall is, what is the soil condition, if there is a geotechnical report. If no, we got to start somewhere by having some assumption, assume soil parameters. From there, we can have the layout requirements of the blocks in terms of whether you need a mass extender, no mass extender, whether geogrid structures will be more suitable for certain heights. And we can generate multiple cross sections in this case for that particular project. And from there, our sales team can come up with some estimation in terms of how much that project will require in terms of the supply of the systems. Then when it comes to the next stage where the client has decided to proceed with the systems, we can offer a proper elevation drawing with more accuracy in that case now, because this is more closer to the construction stage in terms of the types of blocks required with the generation of the elevation. So that's something that we can do, and this is part of our service without charge. The only thing that in Australia that if necessary, if this is not an engineer client that we are dealing with, that a certification is required. Because of our role as a material supplier, we cannot certify the system. So in that particular case, we would recommend a third-party engineers, and that comes with a certification charge. Okay, and we can discuss about that when the project is coming to proceed to the next stage. I hope that answers.
Thank you. Thank you, Eric. Thank you for that. That was a great answer. Liam, bringing you back into the conversation and just returning to Curry's question, and Curry's watching from Victoria, asking you, Liam, what's the biggest mistake engineers make when designing modular block retaining walls? Thanks, Liam.
No problem. Honestly, I think the biggest mistake is underestimating drainage. So in 2016, the NCMA published a report, and they estimated that 90% of wall failures or walls that came down was caused by water. So it's easy to focus on geometry, loading, geogrid, layout, and everything, but unless you get the water right, it doesn't matter. I would say drainage has to be managed properly. But I mean, one of the key points I would communicate, that would be communicating with suppliers and understanding what type of non-wovens or geosynthetics or drainage composites you should use, particularly if you're working in areas with clays or soils with a high fines content. They generally tend to hold a lot more water, build up more hydrostatic pressure. So you want to look at how you can filter that and let the water get away, or look at replacing poor soils with better draining material. And then another core benefit from using, let's say, non-wovens or composites is it stops the migration of the fines materials into the drainage material, which can cause your drainage columns to clog up, and then that allows water to build up over time.
Thank you, Liam, for that. Liam, I might stay with you for the next question, which is coming from Alan, watching from Victoria. We've got quite a few people watching from Victoria asking, what is the significance of using PMB in construction over conventional construction technologies, such as what is the environmental impacts? Liam.
So this is one of my favorite questions because it comes up a lot. It doesn't matter where you're discussing about construction, whether it be in Europe, the USA, or Australia. It's a common question. I'd say one of the biggest advantages with precast modular blocks is the speed of installation. So a lot of large projects, retaining walls are on the critical path. Any delays with retaining wall installation can impact the overall project timeline. Because PMD is installed so quickly, it allows for faster installation with less men on site. And that allows you to keep your project on schedule, but also reducing labor costs. Looking at the environment, precast modular block walls have a smaller footprint generally than other conventional systems, which means you have less over excavation and also less fall off site, which can be one of the more expensive aspects of a construction project. Also, when you reduce your trucking volume, you're reducing your carbon cost. But then, from a sustainability perspective as well, I always tell people to look at asset management. So we produce our blocks generally with a 30 to 40 MPa concrete, which can be designed for up to 120-year service life. So unlike a lot of other systems that might need to be repaired or maintained or replaced with a 30-year cycle or 50-year cycle, PMBs can provide longer-term reliability and sustainable solutions, meaning they significantly reduce the need to remobilize crews and reconstruction within that 30-year window, which mitigates or reduces the largest or one of the largest contributing factors to the carbon cost of a project, which is the installation phase.
Thank you, Liam, for that. We've had a great question that has come in, Eric, from Martin, and Martin is watching in New South Wales, asking you, Eric, for gravity retaining walls generally, designs look at a constant wall cross-sectional depth for the full height of the wall. Can the panel give some insight into the design approaches for walls and reducing section thickness from bottom to top of wall, i.e. pyramid style? And Martin says, thanks. Eric.
Right. Thank you. This is a great question. And I can only say, as lateral earth pressure, the lateral earth pressure, if you follow Rankine formula, is half Ka gamma H squared. So the pressure becomes exponential or quadratic as the height becomes greater and greater. Therefore, there is a cutoff line between how much a gravity alone system can do versus a reinforced soil system, simply because the H squared, the lateral pressure becomes greater and greater. There is so much the gravity can do. But if you take away that difference between gravity and reinforced soil, and we focus only on gravity for now, the type of inverse, i.e. the narrow width base and the greater width at the top for gravity, only possible in this case when you have a situation whereby you need to build a retaining wall of a certain height. Pick a number, say 4 meters high, where the bottom 2 meter is of competent rock material, okay? And you can do something about a narrow width gravity block, say for example the standard block, fill it up with concrete or no fines concrete, and then as the as the existing ground or rock goes up beyond 2 meters, it starts to taper into say a 50 degrees type of a rock slope condition, and you wanted to fill the upper portions. This is where you have this inverse situation. Okay, so in other words, bottom with a normal standard block situation, and then upper 2 to 2.5, 3 meters, you can construct a gravity system, say for example, with a wider mesh extender. That is the only situation I can think of for now that scenario exists for gravity system. And this is also kind of like a combination type of a hybrid system, which requires specific designs or specific type of analysis time, and not the standard gravity or reinforced soil. Okay. Now, on a reinforced soil, just a little bit more comments on reinforced soil. There is a section on geogrid reinforced soil where, again, coming back to a very competent foundation ground, some kind of a competent ground up to a certain level. This is where you can construct a shorter reinforcement at the base up to 40% of the height, slowly, gradually increasing the reinforcement length to 55% and 70% minimum as you build the wall taller and taller. And this is termed trapezoidal shape structure in reinforced soil wall design. Okay, I hope I cover the questions.
Thank you for that. Thank you for that great answer, Eric. Liam, we've had a great question come in asking you, do you provide technical design information for engineers, or is the system exclusively designed by you or your partner companies as a proprietary solution? Thank you for that.
Yeah, thank you. And that's actually a brilliant question to ask, because it's absolutely not proprietary to us. Our main objective as a product developer and a product supplier through our network in Australia and New Zealand is to provide resources and tools that engineers can use to, I would say, confidently provide designs. So our main objective is to support local engineering offices and firms rather than hold that sort of information for ourselves. So I'd encourage people to reach out if you have a project, and even if you just want a sort of free service support to get an early stage preliminary concept, you can email us anytime. We're more than happy to help you. We'll ping over a sort of simplified proposal that you can then take in internally and work on and develop a more complex or comprehensive solution.
Thank you for that. We've had a question about the standards, Eric, and it's coming from Ian and asking you, Eric, does your proprietary design software incorporate analysis and design for geogrid reinforced retaining walls for Australian standards and or New Zealand standards? Thanks, Eric.
Okay. The current free software from Veri-Block covers the National Concrete Masonry Association's design methods, NCMA, which is limit equilibrium. In other words, a lump factor of safety method without imposed factors or partial amplification factors. And also covers the AASHTO limit state method as well. Currently, there's no plan to include the Australian standard AS4678 in this version of the free software. However, as Liam mentioned earlier on in his presentation, there are third-party software partners that is incorporating the Veri-Blocks into their softwares that covers AS4678. For example, Geo5. Yeah, Geo5 is in the process of incorporating that AS method into their software, and this is what we've been told. The launch for having the AS in the software is going to be end of the year, more or less. Okay.
Thank you for that, Eric. Eric, please. Liam,
Liam, do you have something to say?
Sorry, though. Yeah, no, I was just going to add. So Geo5 are hoping to have that standard introduced by the end of the year, as Eric mentioned, but also I believe Rock Science RS Wall does currently have that standard included in it, and the Veri-Block units will be available on that from August. And then I believe Vespa are also working on having that done quite quickly.
Right.
thank you.
Thank you.
Thanks, Liam. Liam, just staying with you, we've got a question from Ramesh. Good afternoon to you, Ramesh, asking you, what are the material specifications of blocks? Are they reinforced individually? Liam?
Actually, there's no reinforcement at all. They're mass concrete, no steel reinforcement. We have a minimum specification that our producers work to, and that's a 28 MPa concrete, although I would say 90% produced with a 40 MPa concrete. The 28 is what we use as a weaker material specification when running tests to ensure that there's always a significant safety margin with the actual end product. Then, apart from that, because it's wet mix concrete, it can be produced to local requirements or project-based specifications. So our minimum is the 28, and then we have our tolerances as well that are indicated on our literature.
Thank you, Liam. Eric, we've got a question coming asking you, how about the joint in between the levelling pad and the retaining blocks?
Okay, there is no joint between a leveling pad and the base block. The base block, or after the leveling pad has been compacted, usually made out of a crushed stone material. If you want, you can put a blinder sand material just to get for leveling purposes. Okay, and the blocks just lay directly on top of that. No joints, no connections. It's a leveling pad.
That's great. And Eric, just staying with you, a question from Ravi asking, do we need to do a global stability check as well for GeoGrid reinforced soil wall?
Whether or not a global stability check is necessary or requires comes down to a few things from my experience. One, obviously, there is a downslope, then more than often you have to perform a global stability check. Two, you are suspicious of the ground condition, foundation soil material, because if the foundation is weak, even though the ground is flat from the toe onwards, there is a chance of potential for slip circle failure, global stability failure. And obviously, when the wall becomes tall, right, yeah, you will want to ensure the global stability is performed anyway, because tall wall is an engineering, it's a higher engineering risk, basically, when the failure occurs. So in a nutshell, yes, generally, and nowadays with the advancement of the software like Veri-Block, Veri-Grid software, performing an adjacent global stability issue without too much of a complicated ground model type of conditions is very easy to perform. Yeah.
Thank you, Eric. Liam, a great question's coming from Martin, asking you, Liam, can a combination of reinforced soil on lower layers with gravity top sections be combined to allow for location where we'll have new building behind where we need to later excavate footing? Liam, thank you.
Yeah, I would say absolutely. That's actually become a fairly common method, particularly in the USA on DOT projects. We refer to them as hybrid projects. So you'll have an MSE structure at the bottom, and then you transition into a mass gravity retaining wall on top. The reason they're becoming popular is when you have taller walls, so maybe 4 to 7 meters, but you might require 2 meters of clearance at the back of the wall for services like cables or ducting. Obviously, you don't want that to interfere with your GeoGrid. So one of the benefits of working with a large block solution like Veri-Block is you have your MSE at the bottom, and then when you transition into gravity section at the top, the transition is actually seamless. You don't have to change product systems, or it's easier for the contractor to install it. And then when you look at the end product on the low side, it looks the exact same. So the public won't actually see that it's been changed or modified. So yeah, great question, and it can absolutely be done.
Eric, we've had a pretty good question that's come in, just asking, where can we download PDF and DWG files? Can you please share the website? Which
Okay,
we can.
right. This is currently, as a company, GeoFabrics, we deal with multiple different sectors and different type of products. So it is impossible for us to put everything on our website. But the typical drawings that I showed in my presentation is something that we can share free of charge. You can get in touch with me. I think my contact is in the presentation slides. Just send me an email and I can forward through. Thank you.
Thanks, Eric. Eric, we're going to just very quickly do two really quick questions because we are getting close to the end. Question one, Eric, is this type of wall suitable at ground with high water table? And Bikal sent that question in. Thank you for that.
Sure, absolutely. When it comes to high groundwater, submerged wall in this case, one of the things that we wanted to mitigate is obviously trying to get the hydrostatic pressure out. So the suggestion is, in addition to filling in drainage aggregate within the core of the block, it is suggested that at the submerged level, below the submerged level of the water, we suggest having the drainage aggregate added to the back as well. That is something that that we will suggest for submerged wall.
Thanks, Eric. And still on the water theme, Juxi has asked the question, is this type of block wall, can it be designed for the coastal environment, Eric?
Yes. I think the question comes more to do with whether the coastal environment with the saline type of conditions, what is the effects and cost on the types of blocks in terms of durability. As Liam mentioned, this is a wet cast concrete wall systems with 40 MPa concrete. So it comes down to the durability of the 40 MPa wet cast concrete resisting this type of saline environment. Normally, the durability concerns comes with when the concrete has steel reinforcement in it, and the steel may get corroded over time. But because of the absence of any steel in the block, there is no such considerations. So yeah, for this type of situation, the wall can be constructed with a very long design life.
Thanks, Eric. And Liam, one last question to you, coming in from Michael, asking you, are Veri-Block blocks stocked, or what is a typical manufacture lead time? Especially important given, as you just said, retaining walls are typically critical path. Thanks, Liam.
The blocks are definitely stocked. Your local manufacturer and producer will aim to have about 20% of their annual turnover on hand at any one time. And the purpose for that is to be able to provide quick response to emergency repairs. If you get a failure or a slip along the road, generally governments or municipalities want to get that road open within as short a period as possible. So being able to quickly respond to that and supply blocks is part of I would say, one of the key advantages of working with a large block solution. On larger projects where you're talking maybe 7,000 square meters, I would encourage you to speak to your local manufacturer so they can look at a production schedule and also delivering on stage and on site to accommodate the installation process rather than having 7,000 blocks sitting on site that might get damaged or mixed up. You want to try and coordinate your staging with delivery.
Great, thank you. Thank you for that, Liam. We have run out of time. The Q&A has gone really, really quickly. but it's all the time we have today. So please join me once again in thanking Liam, Donahoe and Eric Yu for their time and input. These presentations do take a lot of time to put together. I'd also warmly like to thank Engineers Australia's industry partner, Geofabrics, for their support. Just quickly, pleased to share that Engineers Australia's Excellence Awards 2025 nominations are now open. We've talked a lot about engineering excellence this afternoon, so help us recognise the people and the projects driving innovation. You can nominate yourself, a peer, or a standout team by scanning the QR code. As always, we're always looking to ways to improve and plan for future sessions. So if you could spend a couple of minutes completing a short feedback form, which is linked in the description box below. Thank you again for joining us, and I look forward to seeing you at our next Industry Partners event. Thank you and good afternoon.